is the Kozai layout. These simulations can be performed typically on like a few 10 orbital periods. So provided this precession occurs on this time scale.
Yeah, I guess it depends on the orbits. Like it's typically on the order of like something like 10 years. Or depends a bit on the configuration of the system. But I think that there are hints that this might also play a role in the accretion process.
In some of the systems, 10 years is going to be like 50-ish orbital periods, so that's not out of reach. Clearly.
Amazing. Okay, great.
Thanks.
Okay, so if we thank the speaker again.
Yes, that's true.
And the final talk for this session will be by Kaushik on interacting massive main sequence binaries.
Can you hear me? Okay. Hi everyone, I'm Kaushik Shen and I'm currently a postdoc at the Nicholas Copernicus University in Torun. And today I will talk to you about some observational consequences of massive main sequence binaries that are interacting. So I have this nice bag of chocolates here for anybody who can tell me the connection between Batman and eclipsing binaries. So, so it's actually Ras Al Ghul. So thousands of years ago, people looked up into the night sky and they saw that in their stationary picture of the heavens, there were some objects that were changing in brightness. So they were very terrified of it, and then they called it Al Ghul, which means the head of the demon. And the objects that were twinkling were the demon's eyes. So now, and these Algol binaries were the first ones that were discovered to show periodic variations in brightness. And these were also one of the first spectroscopic binaries to be studied, going all the way back to the 16, 17, and 1800s. And fast forward to the last century, if you look at the masses, and the radii of these systems, you will find that the less massive star is larger in radius than the more massive star. And if you think about conventional stellar evolution, you would expect that the more massive star is larger. And this led to the Algol paradox, where the less massive star is more evolved. And the way to solve this paradox is taking into account mass transfer in closed binaries. And I want to thank Matteo for the wonderful introduction on closed binary evolution already, so I can go through this very quickly. So if you take a 20 solar mass star in a 3-day orbit with a 12 solar mass star, if you want to know when these binaries will interact, you just draw some equipotential surfaces. And of particular importance is this one in the figure of shape of 8, which encapsulates the Roche lobes of the two stars. And during the main sequence evolution, the more massive star will increase in radii, and at some point it will fill its Roche lobe and start a very fast thermal timescale mass transfer, where most of the envelope of the donor will be stripped, and you end up with a stripped star with a mass equal to its initial convective core mass in a binary with a more massive star. And in this phase, the mass transfer rate is much smaller because you have a mass transfer from a less massive star to a more massive star, so the orbit is widening, and you can have this configuration stable for millions of years. And these are what we observe as the algol binaries. Now, why should we study these algols? So if being able to refer to Batman in the second slide is not motivating enough, here are my scientific reasons. So these are binaries that are on the main sequence. So you have the least number of assumptions that you need to make. And we also face the least number of uncertainties when we want to draw conclusions from these algol binaries. Secondly, these are systems that are stable at the nuclear timescale. So we have this unique configuration for millions of years. So we can observe a lot of these systems. Thirdly, these are in short periods, and most of them show eclipses. So these are easily detectable. Then we have a strip donor here, and if we study their surface abundances, we can learn a lot about the internal mixing in massive stars. And last but not the least, these also are found just after the fast thermal timescale mass transfer. So if we want to learn about the more elusive thermal timescale mass transfer, we can learn a lot by studying these algol binaries. Now, with all these ideas in mind, I started my PhD looking for massive algols, and during that time, Laurent also gave me the list of semi-detached binaries from the VFTS TMBM survey that he described yesterday. Now, if you look at the Roche-Loew-Philipp donor masses in this list, the first three of them have a less massive donor, so these are the typical algol binaries. But then there are these last two, which have a donor mass which is more massive. But since this survey was a kind of a almost complete survey, unbiased complete survey of massive stars in the Tarantula region, we don't really expect 2 out of 5 semi-detached binaries in this opposite configuration. So thermal timescale should not be able to answer them. So like a really great PhD student, what I did was I ignored them and then went on to compare my model predictions with the observed population of massive algols, where I found a reasonably good agreement. But today, I will not be focusing on these ones. Today, I will be looking into these two guys here. So if you look at the donor masses, they are also the most massive donors. So there might be some mass dependence in these objects and the configuration. So in the era of ChatGPT and AI, I started drawing with pen and paper. So first I show the initial accretor masses as a function of initial donor masses for different initial mass ratios. So this is the entire parameter space in terms of accretor masses and donor masses for binary evolution. And how do we know what is the donor mass after the mass stripping? For that, we need to know that the donor stars get stripped up to the initial convective core mass, which is given by this thick black line here. So fast thermal timescale mass transfer will strip the donors up to this line. So if you have an initial accretor which is above this line, so this will be the typical algol configuration. But if you are below this line, then for non-conservative mass transfer, you can have a configuration where the mass transferring donor is still the more massive star. And you see that at low masses, say at 10 solar masses, this Q limit is 0.4, whereas at higher masses, this Q limit can go up to 0.6, 0.7. So the parameter space at higher masses for this kind of evolution increases. Now, we don't expect all these very low mass ratio binaries to undergo a stable mass transfer. To get an idea of where stable mass transfer will happen, we take help from detailed binary evolution models and draw two lines here. The dashed line shows the cutoff for initial accretor masses above which all our binary models survive a thermal timescale mass transfer, and this dot dashed line shows initial accretor masses below which all our models are expected to merge. Now, between these two lines, whether a model merges or survives depends on the mass ratio. And we also assume that all models below Qi equals 0.2 will merge. So now if we do some coloring here, the portion above this thick black line are the ordinary algols. The portion in blue are all the reverse algols, which I call them, where the more massive star will be transferring mass to a less massive star, and here in orange are all the mergers. Now you see that this parameter space keeps on increasing as we go up to higher initial donor masses. And finally, where do the two VFTS systems lie? If we assume non-conservative mass transfer in those two systems as well, then they lie directly in this parameter space. So this is a direct observational confirmation that this reverse algol configuration is stable at the nucleus timescale. Now, if you think this was fun, finding a new nuclear timescale algol configuration, I would say that the fun is only half done. Now, we can look at how these binaries evolve in the HR diagram. So here I show a 44 solar mass donor with a accretor of 22.3 solar masses. The tracks are shown in color until the donor completes core hydrogen burning, and the rest is shown in gray. The dots are placed at 50,000 years. So what I want you to notice is that before the interaction phase here, the donor will show an ordinary O star-like spectrum, whereas during this fast Kc mass transfer, you lose a lot of mass. The luminosity to mass ratio of the donor increases. The wind mass loss rate increases, and then you can have an optically thick wind where the strip donor can show emission lines and resemble hydrogen-rich Wolf-Rayet stars on the main sequence at luminosities where single stars would not. Now, this is still a bit hand-wavy, and to convince people who look at me like this, so we look at the wind optical depth parameter. So if you take the differential form of the wind optical depth and integrate it for a beta velocity law, and if you take beta equals 1, you can find a form of the wind optical depth parameter which relates to the opacity, the wind mass loss rate, the radius of the star, and the terminal velocity. Now, this is of course an approximation, analytical approximation, but the good thing about this is that I can get all these parameters from my models as well as for the observed Wolf-Rayet stars that we have. And then we can do a consistent comparison. And this is what I show here. So this thick black line shows the evolution of the optical depth parameter as a function of age for the donor star. Now, during this, this is the end of the hydrogen burning of the donor. Now, during this pre-interaction stage, the optical depth parameter is quite low. And then there is this fast Kc phase where you strip a lot of mass and the optical depth parameter jumps by an order of magnitude. Then you have this strip donor phase where the optical depth parameter slowly increases and goes up to 1. Now, what I show in this blue horizontal lines and the red horizontal lines are the optical depth parameters calculated for the observed hydrogen-rich Wolf-Rayet stars. And you see that during the strip donor phase, they are in the right ballpark. And last but not the least, I will show you how our models can explain BAT 99113. So this is a Wolf-Rayet star with a mass of 52 solar mass with a companion of 20 solar masses. And the triangle shows the position of the Wolf-Rayet star in the HRD. The diamond shows the O star, and here I show the best fit model that we have, and we see that it can clearly explain the position in the HRD. Now, the final nail in the coffin is if we can show that the pre-interaction stage cannot explain this star. So for that, I look at the L/M ratio of the observed binary, which I find to be around 4.41. And then I calculate the L/M ratio of our strip donor near this star. And I find that this is around 4.37. And if we compare this to single star tracks at having the same luminosity, we find that it's much lower. So this shows that this star must have gone through an interaction phase where it was stripped by a binary, and it cannot be explained by a pre-interaction binary. And with this, I conclude my talk, and thank you for your attention.
Great. So any questions?
Thanks for this, Kushik. Do you need non-conservative mass transfer in these reverse algal systems, and how non-conservative does it need to be?
I have the same diagram for a conservative case. So if you use conservative mass transfer, then all these lines will come down. So this thick black line will go down to this yellow line, and also these observed ones will go down. But then I don't think conservative mass transfer makes sense for these two observed binaries, because you have to start from a very low mass ratio. So I would say that these observed binaries hint to us that this might have gone through non-conservative mass transfer.
But it's not necessary.
No.
Okay.
Okay. Any more questions, Mathieu? And then.
Hi, that's very nice work. I was wondering, can you say a bit more? Do you include rotation and tides? I suppose you will. And you mentioned that in case A, things are simpler, but I think tides make things much more complicated instead. Like, doesn't that also change how conservative mass transfer would be? What are you assuming for tides?
Yeah, so what our models assume is tides can halt the spin up, so you can have conservative mass transfer at short periods. But then we have these two observed stars, where if you assume conservative mass transfer, then these stars must have originated from initial mass ratio of, say, 0.05, which is really difficult. So I would rather say that we should take the observations and then modify our models, rather than say that case A, short periods must be conservative.
Thanks, that's very interesting. Could you talk about the expected future evolution of these?
So if you are talking about black hole masses that will be formed, or?
What's going to happen next, right?
So this will evolve in the typical way that Ilya showed in or Thomas Tauris has in his binary evolution scenario, when the more like the strip donor will either explode or collapse into a black hole, and then you have this high mass X-ray binary phase, and then it goes on. But one interesting thing that might happen is there is also this small region here where you can flip the masses of the black holes that are formed. So you can have a more massive black hole formed first than the less massive black hole. And that can have implications for gravitational wave progenitors.
Okay, I guess I was wondering if you expect the donors to expand again, but you're saying no.
Yeah, they will undergo a case AB mass transfer just after the main sequence, yeah.
All right, thanks.
Okay, with that, I think we thank the speaker again.